Okay. How did it go with Dr. Gainanova on Monday and Wednesday? Is it okay? I understand that she talked in this chunk of notes, and I wanted to revisit it and then finish up with it actually today. I'll post homework solutions soon, and we'll have another homework assignment that's posted. I haven't thought about the timing exactly, but it'll be up in the upcoming days. It'll be another predictive modeling kind of exercise. So your previous homework was fit a regression model, use cross-validation to tune it. So let's do another couple of examples in your homework. You have a bunch of tools now for predictive modeling, depending on whether the response variable is numeric or categorical. There's different sets of tools. With a numeric response, we can work with a model like this, a linear regression model. And if it's categorical, then we have a bunch of other tools like LDA, QDA, naive Bayes, and so on. So this chapter is about further tuning your model, so to speak. So you have a response variable that you want to make predictions for, and you have a collection of predictor variables to use. But as we now see, there's lots of different models that we can use. Should we use LDA? Should we use QDA? Should we use naive Bayes, or what? Which is the best model? Given a particular model, suppose I want to use a linear regression model for modeling. If I have a collection of predictor variables, I still can consider maybe there's a best subset of the predictor variables that I should use instead of all of them. Or maybe there's a better way than linear function to represent them with. So this material is about when you have the response and you have a model selected and you have a collection of predictor variables, fiddling with that model, in particular simplifying that model to tune it to best accuracy. So one example of what we would do here is if we have P predictor variables, we might consider, what if we choose just the best 10 of those P? I have 2,000 predictor variables in my spreadsheet. Might there be a subset of just 10 of them that give me just about as much accuracy as the 100? Simplifying the model in that way would reduce the variability of the model. And if you remember the way we characterize the overall goodness of a predictive model in terms of mean squared error, which is bias squared plus variability, or variation of the result. Simplifying a model will reduce the variability of it. So generally speaking, if there are predictor variables that aren't essential for use in the model, we will have a more accurate model if we remove them. So imagine that we have a linear model that we're considering. We have a numeric response, like in the genetics world, there's a type of study called Genome-Wide association studies. And what they do is they measure a response variable that is some physical phenotype, like BMI or survival time or whatever, some numeric quantity. And then they model it in terms of predictor variables that are basically categorical variables for a bunch of genes or locations along the genome. So you might have response being survival time and 200,000 little markers, call them markers, predictor variables. And you might have only a dozen or a few dozen samples. So talking about, in that case, something like we have Y, that's, say, survival time, the numeric response, and we have a collection of predictor variables. And in many modern data sets, genomics data sets are one example, you have that N is much less than P. That is, you have fewer samples than you do variables. The multivariate statistics techniques that we learned earlier in the semester, t-squared tests and multivariate ANOVA and such, those will break if we have this scenario, or they can break. Most classical multivariate statistics are designed to work when we have more samples than we have variables. So if we do have potentially too many variables, I have 30 observations, but I have 200,000 variables, we might consider, what if we reduce the 200,000 down to a smaller number? So suppose I want to consider this type of relationship. Number of predictor variables and a measure of accuracy. We might say mean squared error. I could just use one of my variables, or I could use all P. And if we could sketch this curve, then we might find an optimal choice for the number of predictor variables. The model selection stuff that's in this chapter is about doing this. It's about, we have a model. We're going to say that Y equals some particular model of X. Could be a linear regression model, for example. And then we're going to use one of a few techniques to consider different subsets of the predictor variables and score each of them in terms of the accuracy that would result. The result will be, so after doing model selection, we'll have a new model that is simpler than the original one. If it's a linear regression model, the new model will have fewer predictor variables, fewer coefficients to estimate. For a given number of predictor variables for us to consider, suppose we have 200,000 genomic markers in a GWAS study, and I want to make this picture. So I consider a variety of choices for the number of predictor variables to actually use. Let's try 50, let's try 100, 150, and so on, all the way up to 200,000. For a given subset size, say 100, how should you go about picking the best 100? Because if you say, I want to boil my 200,000 down to just 100, then you have to pick which 100. So how should we go about picking a best subset of a given size is one of the principal questions of this material. So if we have a linear regression model like this one with P predictor variables, we're going to consider filtering or shrinking or simplifying this so that we have fewer coefficients. So Dr. Gananova went through, I think, slide 30. And so I won't go through in detail. I do want to revisit this slide. If I'm trying to go from P variables in a model down to a smaller number, here's three classes of techniques for doing that. One is subset selection. And that is exactly what I've been describing, where you start with P variables and you select a subset of P star less than P of those variables. There's no change to the variables. They are they're a smaller number of the original ones. An alternative is called shrinkage. And if you imagine in the case where we have, say, 30 observations and 200,000 predictor variables, imagine the regression model that says y equals beta 0 plus beta 1 times marker 1 plus beta 2 times marker 2 plus ... 200,000 beta coefficients. Let me just write that out. So our model is that the response for individual I is an intercept plus a beta coefficient for marker 1. For our purposes, we could just think of these markers as being binary. They're either on or off. So think of a bunch of locations along a genome, and it's either one flavor or another. It's on or off. I would have a beta coefficient then for all p of my predictor variables, or all p of the markers. Subset selection says I'm only going to pick some of those x's to keep. Shrinkage will look at this model, and instead of picking discretely from the existing p, it will take the beta coefficients and, quote, shrink them by making them closer to 0. So the impact or the contribution of any one of these predictor variables is related to the size of its beta coefficient. So in terms of making the prediction, a covariate or a predictor variable that has a big beta coefficient is contributing a lot. It's got a big vote in what the prediction is. You can decrease its vote, so to speak, by shrinking its beta coefficient. And the extreme would be, if you shrink a beta coefficient all the way to 0, you've essentially selected that variable out. Shrinkage is about shrinking the beta coefficients towards 0. It's essentially like I was describing with the subset selection exercise. It's more mathematically slick, though. Simultaneously, with all p variables, it shrinks the beta coefficients in such a way that the more predictive ones are not shrunk as much, whereas the ones that don't contribute much are shrunken towards 0 and maybe even selected out. That's shrinkage, and there's two main flavors in this material of shrinkage. Dr. Gainanova, I think, finished on the topic of ridge regression. That is a way of shrinkage-based regression. And I'll show you the next iteration of that, which is called the Lasso. Lasso is a real popular term in data science and stuff. It is a shrinkage technique. And then the last class of techniques for doing this, selecting a simpler version of an initial model, is called dimension reduction. And the idea here is to take your original p variables and project them or cram them down into a smaller dimensional space. So for example, what if we took p numeric predictor variables and did principal component analysis and took the top 5 principal components? Instead of 200,000 predictor variables, maybe I use the first 5 principal components. That's not like subset selection, because I didn't just pick individual variables. I created new variables that take my full dimensional space and force it down to a smaller dimensional space. We'll see at the end of these notes that a simple way to do this is just to do where, like I said, compute principal components, and then in this regression model, instead of having beta coefficients times the predictor variables, you have beta coefficients times the principal components. That's called principal component regression. All right. So she would have lectured on the ideas of subset selection. I I mentioned earlier, if I wanted to consider a subset of 100 of my P variables, I would need to define what I mean by the best set of 100. There's a lot of sets of 100. P choose 100, in fact. The ideal way to do that, to answer that question, which is the best 100 predictor variables to use, would be to consider all possible collections of 100. Take every single possible subset of 100, and for each one of them, score it based on an accuracy measure, like mean squared error. And then pick the one that has the best. The problem with that is that that's typically not computationally feasible because there's too many possible subsets. Best subset selection refers to that task of trying to find, if you want a subset of size k, k is less than p, what is the best subset? And that leads to a kind of heuristic take on that optimal solution. Optimally, we would consider every single subset of a given size. That's not practical, typically in practice, because of computational issues. So what you can do as an alternative is a so-called greedy algorithm type approach. And stepwise selection is an example of that. So you may be familiar with forward and backward stepwise regression. That's the idea where maybe you start in this linear regression model. I start with the model that has no predictor variables in it. And I consider in step one, if I were to pick one of them, which one would it be? Which variable, when added by itself, makes the best impact on accuracy? So pick that variable. And then in step two, you would consider all the remaining ones. Which one of them should I add? And you'd repeat, repeat, repeat. And you'd pick the model that had the best accuracy. That's stepwise. You can either do forward stepwise, like I just described, or you can do backward stepwise, where you start with the full model and you consider step one, let's remove one. Which one should you remove? The one that makes the least impact on accuracy, and then iterate. So that's what stepwise regression is. Forward and backward. Let's talk about this for a second. Suppose you have 200,000 predictor variables and you fit a linear regression model, and then you consider some other models that have smaller numbers of predictor variables. So here's my full model with all 200,000, and then I consider a model that only has 50, one that only has 100, one that has 5,000. Training error, or conversely training accuracy, will be highest necessarily on the full model. The more predictor variables you include from your training data, the better you will continue to get on accuracy. So we already know this, but we don't want to choose our model based on just training accuracy. That's why we need to estimate the generalizable accuracy, or conversely, the generalizable error rate, what the authors call the test error rate. Not training data accuracy, but accuracy on test data, like new samples from the population. We've already seen that there's multiple ways to do that. You can make statistical adjustments to things like R squared. The BIC is a statistic that's kind of adjusted for comparing models. And you can do what you did in the homework, which is a validation kind of exercise. You did it with cross-validation, but we could also do a held-out test set for assessing the generalizable accuracy. But all this stuff in this chapter is about considering different models. Should I use all 200,000 predictors, or should I use this subset or that subset? And in the process of picking which one to use, we have to make sure we are using the right metric for guiding that. Otherwise, we'll overfit the data like we've seen before. These are some examples of statistics that are specifically designed for this process. They're kind of adjusted for making multiple comparisons of models. I'll leave that. Okay, so that was subset selection. Let's talk about the shrinkage idea, where we're going to leave all the variables in the model, potentially. We're going to shrink, though, the coefficients towards 0. This is the kind of messy math representation of it, but let's look at it for a moment. The top expression says RSS, root sum of squares, or residual sum of squares. And this is basically the sum of the squared differences between the true response and the model-based representation of the response. So for a given fitted model, if you got the residuals from the model, truth minus fitted value for every individual, and square each of those and sum them up, this is an overall measure of how different the predictions are from the truth. That's the standard objective function for fitting a linear regression model. That's what we would usually work with. What the shrinkage is achieved by is modifying this objective function. So down in the lower expression, it is exactly the RSS plus an extra term. So this is what was up above. That's the residual sum of squares. And then we add in an additional term. It's RSS plus what we call a penalty. This penalty term is a constant lambda times the sum of the squared betas. So remember that the bigger the magnitude of the beta, the greater the impact of that predictor on the overall prediction. And we can minimize the impact of predictor variables, shrink them, by forcing the betas to be smaller. So this quantity, this sum of the squared betas, is going to be big, but get smaller if you shrink the betas. If you take some of the betas at least and force them closer to 0, this sum is going to get smaller. Thinking of this whole thing as an objective function that we want to minimize, let's find betas that minimize this quantity. We need to balance the accuracy of the model with respect to the response, RSS, but we also need to balance not allowing too much magnitude of the betas. The bigger lambda is, this needs to be bigger than or equal to 0. The bigger this is, the more we will shrink the betas. The more aggressively they'll be forced towards 0, and the more likely it is that at least some of them will be shrunken all the way to 0. So let me go forward to the lasso. The lasso is exactly the same idea. It's let's fit our regression model by picking the betas according to this objective function. RSS plus, again, lambda times the sum again, but now these are not beta squareds, but they're absolute values of beta. So seemingly slight change to the way that it goes forward, but it ends up having a nice consequence. Ridge regression and lasso, though, are conceptually the same thing. Penalized regression. The nice thing about the lasso is that because of the nature of its penalty, by using the sum of the absolute values of the betas, it has the ability to actually shrink betas all the way to 0. Ridge regression will always leave the betas at some potentially really small non-zero quantity. And if the goal is, if we would like to result in smaller numbers of predictor variables, if we would like to do some feature selection, then it would be beneficial if this technique would automatically select for us. And because the lasso allows the betas to go all the way to 0, it can do selection for us. As a general tool, if you have a regression model that you're going to use for prediction, whether it's linear regression or logistic regression or any regression for mostly, if the goal is to tune that model because you have too many predictor variables and you think maybe you can do better with a smaller number of predictor variables, the lasso can be applied. Lasso can be applied to linear regression, generalized linear models, so logistic regression, and all types of things. It's a general technique, and it's used a lot in practice. This is just a picture of that illustrates how shrinkage works. Okay, so here on the left panel, we have lines or curves for beta coefficients. So there's a particular model for this credit data set that has a beta coefficient for this variable, beta coefficient, and so on. On the x-axis is the penalty term, lambda. I said that the bigger you make that, the less magnitude of the betas you will see. It'll force more shrinkage. So as lambda increases, you see these beta coefficients going to 0. They're shrinking. In some cases, there is a little bit of increase where you wouldn't expect it. They're not necessarily all going to decrease in magnitude monotonically. Overall, they're being penalized and forced towards 0. So most of the time, you're going to see them tracking towards 0 like this. The bigger lambda is, the more shrinkage is done. So suppose we're going to do linear regression, and we have a numeric response. We have 200,000 predictor variables, and we want to use the lasso to do model selection for us. The tuning question, there's always a tuning exercise for a predictive model. With Lasso, the natural tuning parameter is lambda, the shrinkage term. Should we pick it to be 20? Should we pick it to be 100 or 1,000 or whatever? What technique do you know of already that could be used to pick the best lambda? If you were going to fit a regression model and use the lasso, to use the lasso, you have to pick a lambda. For a given lambda, it'll give you back modified shrunken coefficients and your simplified selected model. I don't know what lambda to use, though. So what I could do is consider a bunch of different choices of lambda and then use something like cross-validation. If I were to use cross-validation, loop over CV folds, and in each loop, consider a bunch of lambdas, average over the CV folds, and I would have a reliable estimate of accuracy that would go with each choice of lambda. And I would pick the lambda that gave me the best accuracy. I'll definitely have you do the lasso in your next homework, so you'll do that process. What is the optimal choice of lambda? Okay. If you're interested, it's kind of an interesting question. Why is it that ridge regression doesn't actually select out features and Lasso does? There's some interesting concepts. I'm not going to go through it. If you're interested, check out these slides. This slide 41 speaks to what I was just talking about, choosing lambda, selecting the tuning parameter for a shrunken regression model. The R package that implements Lasso, that these authors provided, has a built-in cross-validation tool. So they propose that generally you use cross-validation for choosing lambda. And they have a built-in function that will give you the picture I was describing, lambda, some measure of accuracy, based on cross-validation. But you wouldn't want to try different lambdas and get an accuracy measure with the training data, because that's the whole problem with overfitting. You would result in no shrinkage. Shrinking with the training data will always increase the error. So you need this cross-validation, or more like generalizable estimate of accuracy for each lambda. That's why we need cross-validation. So suppose, let me comment on this last bullet point. Suppose we are in that same exercise, 200,000 predictors, and we use the lasso, and based on the cross-validation routine, we get a particular lambda that seems to be best. And based on that lambda, we only have 500 predictor variables left. So all the remaining ones have been shrunken to 0. Then if I wanted to provide my final model as a tool for other people to use, like code it up in R and say, here, if you want to make a prediction, plug it into this function, then what you would do is take all of your training data and refit that final model. In the cross-validation routine, we would have considered a bunch of different lambdas and fit the model with each lambda, but only using a subset of the data because we were doing cross-validation. So the point is, after you do cross-validation, on the basis of the cross-validation, you pick the tuning parameter for your model. Then your final model is fit with the whole training data set, the model with that choice of tuning parameter. And if you're going to code something up and put it on your website as a predictive tool based on your analysis, that's what you would use. Fit it to the training data and use the selected tuning parameter. And let me finish with this part, which is the third of the categories I mentioned. Yes? You asked if did I say if we increase the shrinkage, the prediction accuracy? So if we shrink these beta coefficients, then with the training data, we will monotonically decrease the accuracy with the training data. Because on a training data set, you always want all the variables in there. That's as most accurate as you're going to get. The least residual squared deviation. But with the test error, which we estimate with cross-validation, beyond a certain point, we would expect that shrinkage decreases error, increases accuracy. That's the point. We're considering going from a big number of predictors down to a smaller one because we think that it might result in better accuracy. Imagine that you have so many predictor variables and some of them are uninformative, or some of them are redundant with other ones. Some of them are too variable to be of any use. Removing them will improve the overall prediction accuracy in the general population. Not necessarily with the training data, but with the general population. So we are considering shrinkage in the expectation that at a certain point, this is going to get better. Shrinkage increases accuracy. So I've got mean squared error on here. I should make that, I need to change the label. Not MSE. I'm talking as if this was labeled accuracy. The more you shrink, the less accurate you are with the training data. Beyond a certain point, the more you shrink, the more accurate you are where it counts, which is in the general population. So the other alternative, if it's not pick a subset of the variables and it's not shrink the coefficients for the variables, another alternative is to transform the variables. So take the P predictor variables and transform them, project them, do something to them so that they can be represented with a smaller number of variables. And given what we've covered so far, the obvious way that we would think to do that is with principal components. So, for example, we might consider transformations of the form of a linear combination. I'm going to take my P variables and transform them to some smaller number. One way to do that would be to consider my new variables are just linear combinations of the original ones. Not the only way, but that's one way that you could go about turning your original ones into a smaller number of ones. So the idea is you do this reduction technique. You took your P variables down to M smaller than P variables. And then your regression model uses those new variables as the predictors. Instead of the X's, we would have a smaller number of Z's, new variables. And then you could just fit that regression model and use that for prediction. If you were to do this, suppose you had 200,000 predictor variables and you compressed them, transformed them with a set of linear combinations into just 100 predictor variables. And you want to code up your method for people to use. Whenever you get data of this type with 200,000 predictor variables, you plug it into my function and it'll make a prediction. While your model only has 100 variables in it, each of your variables requires all 200,000 of the original variables to compute. The Z1, the first new variable we discovered, is a linear combination of all the variables. So if somebody wanted to use my function, if I coded it up and put it on my web page and said, upload your data, I'll make a prediction in terms of just 100 variables, I would still need all 200,000 variables so that I could compute my variables. So it's not like we completely eliminate these variables from anyone's consideration. It's just that they're not used as they're not used directly as predictors in the model. So the case where we do this dimension reduction with principal components is called principal components regression. You have P predictor variables, you do PCA on them, and you extract the top so many and use those selected principal components as the predictor variables in your model. Choosing how many of the principal components to use is a tuning problem. Just like tuning the lambda parameter, tuning a probability threshold with logistic regression. With principal component regression, we have to tune on how many principal components to use as predictors. And there again, we could use cross-validation or a held-out test set. All right. Oh, this is interesting. A more advanced approach to dimension reduction with a model is called partial least squares. Principal component regression takes the predictor variables and does PCA on them. But by doing PCA on the predictor variables, it's not factoring in the response variable at all. Replacing the p variables with principal components, you can count on that to be a more compact representation of the x's, but it's not necessarily going to improve the relationship with y. Principal component regression, put another way, is not designed explicitly to increase model accuracy. It's all about just reducing the predictor variables. So if we could instead simultaneously reduce the prediction variables while benefiting the predictive ability with respect to y, we could probably do even better than something like principal component regression. So that's what partial least squares does. So principal component regression, that's what these bullet points are saying, is that principal component regression summarizes the predictor variables in such a way that does not use or pay attention to y. Y is not used. So it's not a supervised selection process. It's not a supervised dimension reduction process. So the consequence or the penalty of PCR, principal component regression, is that just because we represent the predictor variables well with a small number of PCs, we don't necessarily increase the model prediction accuracy. So that's where partial least squares comes in. And here's the basic idea. Partial least squares identifies new features. Principal components identifies new features. They're the principal components. Partial least squares is going to find its own new features, but it does it in such a way that makes use of the response y. So it finds new features that represent the old features well, but while requiring that the discovered features are related to the response. So it's kind of a balance between finding new features to explain both the predictor variables and the response. And predictably, partial least squares usually is more accurate than principal component regression. Another, I'll finish with this idea. When you have a lot of predictor variables, if you wanted to use some of the multivariate techniques that we've seen that don't work well when you have p much bigger than n, so suppose you have 30 observations and 200,000 predictor variables, and you want to do a t-squared test or something. In order to do those multivariate inference and LDA type, inference type things, we have to work with a covariance matrix. The capital sigma plays a big role in the t-squared statistic and in the MANOVA stuff. And in particular, we need to be able to invert that. If you have 200,000 variables, you'll have a 200,000 by 200,000 covariance matrix. And if you only have 30 observations to work with, those observations are going to get kind of overused in filling out that enormous matrix. So what you wind up with is highly variable entries in the covariance matrix, and it can result in computational problems where you can't invert the thing. So you can't use the techniques that we've seen in the earlier part of the semester. So one modern technique for addressing that is the idea of sparsity and trying to enforce sparsity in a covariance matrix. What I mean by that is, imagine the original 200,000 by 200,000 covariance matrix. Potentially, every single off-diagonal element is different, is unique. We could simplify the number of parameters in that thing if we enforced some relationships, like, for example, suppose we said that all the off diagonals were a single number. That's a huge simplification. But we could, between the extreme where they're all unique and they're all the same, there's a bunch of in-between areas. So there's a lot of modern research these days in statistics into how to take that 200,000 by 200,000 raw, really messy covariance matrix that you computed with just 30 observations and adjusting it so that it's much more stable and it's more, quote, sparse. There's fewer components to it. There's fewer parameters that have to be estimated. So suppose you had data like the 30 observations and 200,000 predictor variables, and you wanted to use something like linear discriminant analysis. Linear discriminant analysis uses a covariance matrix in it because it's a multivariate normal-based model. And there's a covariance matrix and an inverse of one in the function for computing posterior probabilities. So if you tried to use LDA with that data set, 200,000 predictors and n equal 30, it would probably give you an error, like can't invert sigma or something like that. What you can do in practice is a variety of things. You could use the things that we just considered, feature selection. Let's go from 200,000 to a smaller number of predictors. You could also force the big giant covariance matrix to be simpler using sparsity type methods. So I won't have time to lecture on how those actually work, but just FYI, if you're in the real world and you want to do LDA to do prediction, you've got too many variables, it gives you an error. There are things you can do in order to kind of nuance or massage your data to work with that model. Okay, I will stop there. Any questions on what we talked about? Okay, thank you. I will see you Monday.